second class for mechanism design. This lecture is being recorded, and inshallah I'll share the recording with you as soon as possible. Okay, welcome to all of you. I hope you have gone through the first lecture. If you miss to be together on the online session, I hope you went through the recording, the YouTube link that I have supplied. Do you have any question for so far? Mr. Patterson? Mr.
No, Doctor.
Mr.
No
Tan?
questions so far.
No question, Still too early. Okay,
Yes.
if that is being said, let us proceed. Let me share my screen. If I can do that. Entire screen na senang. Okay, so I'm not sure where we stopped last time. All right. Okay. If we go to this page 14, we have linkage mechanism. So there are many type of mechanisms. Even things that we have learned before, such as gear system, belting system, chain. Those are all mechanism as well. And those are rigid body mechanism. And rigid means they don't deform that much. I mean, everything deforms actually if you look into the minute scale. But in a bigger scale, from a wider perspective, if things that are hard, uh, we consider them as rigid. So the shape of it, the overall structure of it do not change as we turn this thing as this thing move, either in translation or in rotation. So the shape will still maintain the same. So those are rigid body mechanism or rigid body linkage. But linkage is another type of rigid body. So they are just like what we have seen this one. So all these things just links. So this is one link, this is another link. Okay. Even the hydraulic cylinder, hydraulic actuators can be broken into two links, the cylinder part and also the rod. So all this, so if you look at all these things, they do not look like gears, they do not look like all these the other things that have specific a lot of other schools, I guess, skip this part because it's kind of hard, but it's actually very useful, and we see this a lot in a lot of machines. That's why it is important. That's why I personally took an effort to include this kind of things, because previously we do not have this topic in mechanical design, but I took it upon myself to include it. When they say they want to revamp the old curriculum, so I said we want to change it from the chapter. in one of the chapters in mechanical design. So yeah, so this is something that not only for students who are taking mechanism design, but other mechanical engineering students should also learn this thing. At least the basic parts. Okay, and I believe you have seen this stuff before. But other than rigid body mechanism, we can also have compliant mechanism. Okay, compliant mechanism, they are not being made using rigid bodies. They are flexible bodies. So the components are made from some kind of plastics or even metals that can bend rather than hard to bend. So so a lot of they are made to be much simpler, a much simpler machine. So compliant mechanism, we possibly do not need the complex type of joints. Yeah, maybe you're talking about different kind of joints. So instead of a real joint, pivot joint, or sorry, revolute joints, we might have some they call it pseudo unfortunately, I do not include it in this class. So, but if you have the interest, you can go look it up. There are uh, tons of resources that talk about or deal with compliant mechanisms. Um, most of the work is being done by groups led by the professor in Brigham Young University in Utah, and also University of Michigan in Ann Arbor, Michigan. So another type of mechanism is the robots. Robots. We are not talking about R2D2 or but yeah, if R2D2 is a real robot, so that can be also included. But usually our focus is more on the industrial robots, robots that can be used in industrial settings, such as for pick and place and for doing welding, and also to do uh, pick and place welding, and a lot of other painting also can be done by using robots. So those are mechanisms the regular linkage mechanism as opposed to robots. Robots, you want it to be more as much flexible as possible. So the meaning you want robots to have high degree of freedom, DOF, whereas linkage, you want to minimize the degrees of freedom. Okay. So for example, this machine over here, or this part represented by this kinematic diagram over here. So how many degrees of freedom does it have? So we can tell that by counting the number of actuators, numbers of actuators. So in this case, we have 1, 2, and a hidden 3 over there. So 1, 2, and 3. So these are the actuators. Penggerak, in Malay we call it penggerak ataupun things. So the other uh, more popular types of actuator is the machine. Motor, electric motors especially. So motors are usually used to move something, to rotate or an arm, or to cause some um, earth movers like this one, like this excavator or backhoe. Okay, so by the easiest way to determine the number of freedom is by identifying which are the how many how many actuators are there in the system. Okay, so in this case, 1, 2, and 3. All right, so that's the most basic one. So meaning the operator over there in the cab will have to control basically these three actuators in order to operate this machine. Okay, you understand that? Okay, so I hope that makes sense. Um, but if you do not want to measure that or uh, to determine the number of degrees of freedom by that way, by looking or identifying number of actuators, what other ways to do that, to achieve that? So the other way is the calculate through calculation is by using this. I guess if you search for Grobler's equation, they might give it in a different form. But the form that you want to use is this one. F. Either we use F here for freedom, or we can also use M, small m, for mobility. It's not the same as the mobility program that some of you guys participated. But this is the mobility of the machine, of the mechanisms. In how many ways does it able to move freely? In how many ways does it can it move independently? Okay. Okay, some movement, even though you see all the other links move, but actually they are not independent. So meaning one movement from this one will move the other link accordingly. So meaning the other link is not independent from the first one, I guess. Okay, but when we talk about freedom, we want to see in how many ways they can work, move, or rotate or translate independently. Okay. Uh, Easiest way to see that is to think about it is in your own body. So if you think about it, your left in fact, even if you look at one arm, your fingers are independent, can move independently. If you put your arm in a certain orientation, your elbow, your arm, your hand in a certain angle, but still each of your fingers can move independently. So meaning we as our human body have a lot of degrees of freedom. So we have a very flexible degrees of freedom. That's why we are capable to do a lot of work, unless you are very lazy, just want to sleep in your bed, especially here in the Ramadan. If you think you are too lethargic to do anything. Betul kan? Amirul buat apa tu Amirul? So actually we are very capable to do a lot of things because we have high degrees of freedom. Of course, we are not as strong as this machine, but in terms of degrees of freedom, we are way much better from this machine. Okay, we are more flexible than that. Okay, but back to this equation. So F. So this is why in the previous class we categorize the mechanisms into, especially the joints for the mechanism into J1 or J2. I hope you still remember that. So J1 will be number of primary joints, and primary joints will include only two, either uh, revolute joint, or sometimes we call it, or oftentimes we call it pin joint, revolute joint or pin joint. But the symbol is R, R, and then we have the other part is prismatic. If we have sliding, so we call that prismatic joint. The symbol is P. So R and P joints will go into J1. So you have to count the number of J1s. Usually we have a lot. Then we have J2, number of higher order joints. So J2, we have J2 if we have gear, or we have cam and followers. And then we have screws. And then the fourth one will if we have pin in slots, pin in a slot. This analysis to find the number of freedoms. So usually, if we find that the degrees of freedom is 0 or less, or a negative value, so it means it is lock mechanism. Lock mechanism meaning is basically a mechanism, a structure or a truss. So it's not supposed to move. Okay. So like usually if the links is forming triangle, so a triangle means it is a structure, basically. Okay, unfortunately I'm using a PDF. Can see the uh, so it's not showing apa namanya. So I think I'll show. There's another sketch over here, just like oh, this one is also not showing the sketch. But I guess last time I showed you the sketch. Uh, Anywho, maybe I have to repeat this lecture on Monday to show that sketch. Because can, but I can also use the uh, the whiteboard. I seldom use that. But anywho, maybe you can try that using the things that I've taught you in kinematic diagrams. Over here we have a, uh ternary link. Ternary link. This is the binary link. This is another ternary link, and this is another ternary link. But over here we have some changes. We have some changes, and fortunately, I cannot. Hold on. Okay. Sorry about that. So this one you can draw that or do the kinematic diagram, and if you want to include this back thing over here, we have a screw, and actually we can adjust the screw knob over here, um, so that this location where the pin is not shown here or is hidden inside the body can be slide um a little bit backward to the right. Can be slide a bit backward, and you can imagine that will affect this lower arm over here, or the gripper, lower gripper over here. So, yep. So I think if it is going backward over here, this will go a bit uh, up over here. So it will limit the way this thing can be open. So if this one to be able to open wider, I guess this one needs to be slide in determining that. Okay, when you do the calculation, for example, this one, when you have your n is 4 and your j1 is 4, so n is labeled in the circle on the balloon, in the numbered balloon, 1, 2, 3, and 4. So that's your n is 4. Number of elements, number of bodies or links, and then j is labeled by the letters. Usually we use lowercase, small letters, but big also can, uppercase, uppercase, aperture. Anyway, so you have A, B, C, and D. So remember, the link is always between two bodies. So like between 3 and 4. So this revolute link is C, between 3 and 4C, and then between 3 and two ones. Okay, so if you plug in this number 4 and 4 into here, so you will get the degrees of freedom is 1. So n 4 minus 1 is 3, 3 times 3 is, and then minus that with 2 times 4, so 8. So 9 minus 8 is, and minus this is 0, because over here there is none of those four things. We do not have a gear, we do not have cam, no screw, and also no pin in slot. So that's why our J2 is 0. So that will give us a 1 degree of freedom. So meaning for 4-bar mechanism, it is a 1 degree of freedom system. That's why it is being studied a lot, and because in essence, a lot of machines that we use in our daily lives will have a 1 degree of freedom system, and usually is either a 4-bar mechanism or a, uh um, slider crank. We can also have a one, and I guess our focus is not for that kind of machine. Okay, so let's take a look at this so-called special cases. So if you have this triangle, each are independent links, but they are bolted, they are fixed or connected with the pin. But here we have n is 3, our f, this is actually J1. So this is from Wikipedia. So I would say, I will label this as J1. J1 is 1, 2, and 3. And thus gives us a m equals to 0, meaning this is a structure or a truss. Structure means there's no movement. It's not a mechanism. Then for 4-bar mechanism, like I said recently, if n is 4 and J1 is 4, we have a 4-bar mechanism. So it's supposed to give us 1 degree of freedom, 1 DOF. And then this is a slider crank, same thing. N is 4, the ground, the crank, the connecting rod, and also the slider. So 1, 2, 3, and 4. And for the both are J1. So this gives us m equals to 1 degree of freedom as well. But once we have a 5-bar linkage, 5 and 5, 1, 2, 3, 4, and 5, and the joint is, we have 1, 2, 3, 4, and 5 over here. So this gives us a m equals to 2. M equals to 2. So you have to go back here, 5 and 5. So 5 minus 1 is 4. 4 times this one is 12. So this whole thing is 12. Minus 2 times 5 is 10. So 12 minus 10, that gives us a 2 degrees of freedom. So this is correct. How does it work here? So you see, if I fix this link over here, this, and this will be as if this one. Okay, it'll turn this 1, 2, 3, and the ground will be just like this one. But if I turn this link a bit to this side, or maybe down here, and this will be a different kind of from this one. So even if I hold this thing, this one is a degrees of freedom. So over here, but if I hold this one and the second one also, I hold, meaning fix, do not move, like I glue this to the ground or something. So this and the ground cannot move. Okay, meaning if I hold two things together, meaning this whole thing will turn into a truss. Okay, if you do not understand, please stop me. I'm not sure if I can make you understand, but I can try. Men can only try. Okay, this next part is a bit challenging to understand, but I guess we can try. So this is not basically is another way, the third way to determine degrees of freedom. Degrees of freedom. So the first way is for you to identify actuators. Okay. The second way is to do through calculation. Calculation, maybe you do not need to uh, degrees of freedom by sys and fix. Sys and fix. So this might not be the easiest thing to understand, but sometimes you have to be able to use this thing because there is no other way. For example, um, if I want to see how many actuators are there, so here from this sketch we are not told how many motors or hydraulic arms are being are being employed here. So there's no cylinder, hydraulic cylinder is not shown, or which part is being connected to the motor. So there's none of those information being given from this diagram. So by using the first method is not feasible. So the second method is KMOGE. So possibly you have to calculate how many links are there. So definitely all the grounds is number one. So this is number 2, 3, 4, 5, 6, and 7 revolute joints here. So they are J1, revolutes are J1. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So 8 over here. So it seems that this thing is 7 minus 1 is 6. 6 times this is 18. Minus 2 times 8 is 16. So 18 minus uh, 16 will give us 2 degrees of freedom. 2 DOF. So 2 DOF, let's take a look at this part. Okay. So this part between here, here, and here, if I seize this part, this whole thing, as if I glue or cement this link number 1 here. So this is a four bar mechanism. This part is a 4-bar mechanism, and then as what we have seen so far, a 4-bar mechanism should be 1 degree of freedom system. So once I stop one link, all the other links will stop, even for this part. Okay, even for this triangle will stop move. It cannot move anymore. So basically this whole thing will become like a statue. It's a structure. Mechanism, can they still move? Okay, can they still move? So you have to identify or recognize what we have left. So what do we have left? So this is part of the structure, or the ground now. So what we have is 1, 2, 3, and 4. So this is another 4-bar mechanism. So 4-bar mechanism, if I stop this link, do you think this link can move? No, they cannot move. So this is has become another structure by seizing one of the links. It's the second link. If you seize it, so this whole thing will become static. So we want to see how many ways we can hold the system, and then to get all the system static, become static. So if we can hold two links and the whole thing becomes static, meaning it is a 2 degree of freedom system. Okay, it's how many ways we can control this thing, and possibly that those those are a good place to put your motor lah. Maybe one motor over here and another motor over here lah. Okay, it is seldom in the ground, in the ground. Okay. Okay, this is another complex one. I'll leave it for you to do this exercise to identify if this calculation is done correctly. But if it is done correctly, uh, the number of n is 10, and the number of links is found to be, sorry, the number of joints found to be 13, all J1. And this whole thing will have a 1 degree of freedom system, meaning if I move one link, all the other links will move accordingly. Accordingly, they cannot move independently. So some will move a lot, some will move just a little bit. All right, in this page 20, sometimes um, when we do the kinematic diagram, we can simplify things uh, like this one, and at the same time also connected uh, link 4. Alhamdulillah. And it seems that it's trying to tell us we only have to use one pin, one big pin to connect all the three links labeled 2, 3, and 4. Okay, I hope you understand the situation over here. But the truth of the matter, we doesn't regardless of what the physical situation is, the analytical situation will be the link is between two bodies or two links. Okay, the joint is between two links. Let me say that again. We define joints is between two links. Okay, so this joint you have to double count. So the first joint will be between 2 and 3, and the second joint will be between maybe 2 and 4, or between 3 and 4. Okay, so you don't have to triple count it, or one is between 2 and 3, and then 2 and 4, and then 3 and 4. No, it's not enough to say. So we take the least number of way to connect them. So it's uh, so between this body 8 and 6 and 9, they are connected at 3 points here. 3 points, and we have another body called 7. Actually, we can put them together, like you crush or simplify this thing. So links F, what is this? Is that E, F, E, and H can be simplified by using a big pin instead of small pins. So you have big pins, and that will connect link 8, 6, and 9 together. So that will simplify it a little bit. But at least in the analytical stage. So so here we have basically have two J1s. Okay, one is between 2 and 3, and then between maybe 3 and 4. Okay, and same thing here. So we have a link, a slider, and also another link. So in this case, we have to double count, double count. Okay. Over here ada tak yang kita kena double count? Okay, mungkin we'll see another example later on if we cross that bridge. Okay, so what is this thing? It's called the tractor, and some tractors can be attached with this kind of we call it front loader. Front loader. So we have this tractor and attached with the front loader. Okay, front loader making this thing able to, instead of just pulling something at the back, we can also do work with the front part to move some dirt, some earth, okay, up to the lorry or to the truck, dump truck. Represent it with with a with a with a what? With kinematic diagram. We call it kinematic diagram. So kinematic diagram will simplify things, and you'll see here the one attached to the frame is going to be the ground. So we have this part, this pin attached to the ground, and also this pin attached to the ground. Then this boom will have one pivot, two pivot, uh, three pivot, and also four pivot. So this is a quaternary link. So you can draw it any way you want. It might not look as exactly as this physical thing, but as long as you have 4 points for the pins, that'll be fine. Then we have one and two uh, hydraulics, hydraulic actuators or hydraulic cylinders, and then we have the bucket up in front here. Um, front loader, front loader animation, Wikipedia, I guess. Any fan of Thomas? We have Thomas front loader. Mm, yeah, I guess you guys know how it moves, right? Uh, loader animation. Okay. Oh, GIF. link, or maybe it's in the PowerPoint version of the notes. Run loader G. Run loader shift. This one. So let's visit that. So this pretty much looks like that green tractor thingy. So you can see how it moves. Even though from that figure that I in the PDF, we do not really see how it works. But over here in this animation, you should see. So how many degrees of freedom does this have? Anybody? Mr. Tan? So it should be two degrees of freedom. 1 and 2. Like the first way to determine it is by calculating how many actuators there are. Uh, but not so fast. Not so fast. Hold your horses. But you see the other part on the back side of it is just a copy of this front thing. Okay, so when we have just a copy of that, you got to ask yourself, is this doing something else or is it just doing the same thing? So when we have two on one and on left, one on the right, and they are of the same size, usually most likely than not, they are just uh, distributing the force between left and right. Okay, so that way they can use smaller size actuators, some smaller size hydraulic cylinders instead of big one. Okay, sometimes they just have one in the middle and they use maybe double the size or something like that. Okay, hope you understand that. And then we have a bunch of other stuff here, a few more slides, but I guess, is that enough torture for you guys today? Anybody?
We still good, Doctor.
Cukup, eh?
Yeah, we are good, doctor.
We still okay.
How do I stop my hmm, my sharing? You still can see my screen. Okay,
Boleh,
how do
boleh.
I stop? Okay, I'm gonna stop sharing. And do you guys have any question? Tak ada. So what I'm gonna do is I'm gonna try to upload some exercise on the topics that we have just learned so far, and I want you to be giving some try on it. So because this homework, I call it homework lah, but basically it's small assignments. So you have to do this one. When I was a student, usually we have to hand hand in or turn in this assignment or homework, and that will be graded either by the professor of his or her graders. Okay, so and those scores will be counted. material right from the beginning. So because a lot of this stuff, when you sit for the exam, if that is the first time you want to try to solve it, then good luck to you. I think your luck will be much better to succeed if you have done it before, you have solved it before, either through assignment or through project. Okay, so you get what I mean, right? So with that, I think it's a good place for us to stop for today. Again, is there any other question before we leave? So I believe some of you guys have another class to attend. So you guys have a great weekend. I'll see you guys on Monday, inshallah. Take care.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
All right. Thank you, Doctor.
Thank you, Doctor.
Thank you,
Doctor.
Doctor.
Thank
Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Oh, dah hujung-hujung baru ceria punya.
Terima kasih, Doktor. Assalamualaikum.
Okey, sama. Waalaikumsalam. Bye.